I warmly like to welcome Eduardo Reck Miranda to the stage, who will give us now some insights into his work with quantum in the context of sound and music. And he will introduce us also to some of the technological concepts and ideas that he and his colleagues will use in the concert and musical performance later at sometime shortly after 7 here in this room. Eduardo Reck Miranda is a composer and researcher, currently professor at the University of Plymouth and also the director of the Interdisciplinary Center for Computer Music Research, the ICCMR. He has worked extensively on AI in music and also experimented a lot with human-machine interfaces, including, for example, connecting brain and brain waves to musical machines and systems. And recently he has published a book that I can recommend to all of you. It's titled Quantum Computer Music. So exactly all the background that we are talking about. And I also like to point you to one article on our CTM Festival online magazine. You will find it on our website that Eduardo has written for us. It's a primer on quantum computing in the context of the history of computing and sound. So, recommended read. And now, Eduardo, the stage is yours. Thank you.
Thank you. So which button I press? This one. No, that's not the one I wanted. This is the one I wanted. Okay, so thank you so much for being here. It's nerve-wracking to be talking to so many people. What I will do, I will repeat a little bit what Oliver said, an introduction to quantum computing, but from my perspective, from the perspective of a composer who is trying to understand this. And then I will not enter in too much technical details because that's not the objective here, but I will guide you through some practical ways of thinking about quantum computing technology and the way myself and my colleagues in my research center have been thinking on ways to harness it. Because contrary to what the mainstream developers of this technology are working towards, we are not so interested in speed or processing a lot of information or being better or worse. We are interested in exploring what can we do with this sort of machine that is a bit different and that can enhance our way of creating music. And as I will show you a little bit during this presentation, music is a natural progression, I think, in exploring new computing technologies in art. We composers have been doing this since the beginning of the computer itself. So let's go through a few things. I want to start with this. People often ask me, what is it that, what's the main difference between a sequential way of programming a machine and a quantum way of programming a machine? And how would this machine work? So this is, again, a metaphor, a way of thinking. As our colleague Oliver said, no, it's not quite right what I'm going to say, but it's a way into, it's a door to begin to understand what we may be able to do. So this is the Where is Wally or Where is Waldo in the US, kind of cartoons that we give to children to excite their imagination, their curiosity, and the skills of finding patterns and finding elements in complex situations. So you can see Wally just there next to the table there, right? So that's the Wally there, this striped t-shirt guy. So if we ask a sequential computer to solve this problem for us, we would need to ask many questions. Now, probably as many questions as there are people in this figure. We go one by one. Is this Wally? No. Is this Wally? No. Is this Wally? No. No. In the worst case scenario, if Wally is at the bottom here, we would have to ask as many questions as there are people in the picture. But if a clever programmer knows how to harness quantum computation and represent all that is shown in this picture in what we call a quantum state, quite similar to the problem of unlocking the bicycle locker before. We can give this to a quantum machine, build the quantum state, prepare the program in a way that when you make an inquiry, the probability of getting the answer straight away is very, very high. So you would have to ask much fewer questions to the machine to get your answer. If you are lucky, the first time, depending on the quality of the computer that you are using. So that is the potential of quantum computers, to process information not fast, but in parallel, what we call in superposition. Now, let's go back in history. And I want to remind you why music is interesting and why we think we should start exploring this new technology with music. This is how a computer looked like in the 1940s. They were big, as we know, our colleagues already mentioned earlier. They need specialist knowledge to program. It's not anybody who could go to the room and program these computers. There were no keyboards, no monitors, no mouse. So all the programming was by plugging and unplugging cables to make those relays, which are switches to process information for you. And now, since the 1950s, very early on, composers started thinking about, well, wow, there are these machines here. How can this help us to, how can we compose music with them? Because in many ways, musical thinking involves a lot of logic, a lot of mathematics, a lot of formal manipulation of information. That is sound represented in terms of information. And computers are ideal for doing these things. So here you can see the famous John Cage, already in the 1950s, working with Gerhard Hiller at the University of Illinois. He was also a composer, but a professor of chemistry at the time. And they programmed the machines to generate music at this time. Then we've got, of course, Yanis Xenakis. Contemporary musicians are very fond of him because he is one of the fathers of computer music. He is the one that started proposing ideas of using probabilities, using models, using physical models to compose music. And he started building his own systems. In the 1970s, he built this kind of architect table where you could draw sounds, and these sounds then were converted into digital, and then you could hear them. So again, these are composers, creators, hacking the technology, trying to find ways of using this technology that were not for the scientific applications they were being developed at the time. Here again, we have Laurie Spiegel in the 1980s. Already you can see a more conventional looking computer there, the little Macintosh there that was quite classic, at the time, and it still is a nice piece of museum today. And what I want to say is this. In only 70 years, the technology that we have to make music today is incredible. And you know what? Were those pioneer composers who started it, who started thinking about how can we make music, how can we synthesize sound, how can we represent musical notes in terms of binary numbers, and so on and so on. And today we have such an industry, a music industry that is unparalleled. If you think in comparison to other entertainment industries, the music is very big. There is no music today without a computer. That's why I've been thinking about, well, this picture here is better. What will be, what can we do with this in 70 years from now? It's mind-boggling. I mean, it really is. So this is a little comparison I want to make so that we can kind of start thinking. In the 1940s, machines were big, difficult to program. You need specialist knowledge to program. And today, we've got these quantum computers that are being developed and requiring exactly the same sort of know-how to use them. There are quantum physicists today that can program these machines. There is not really a decent programming language yet for programming these machines. And they also need to be kept in controlled temperature, like in the 1940s. There need to be a 20 degrees centigrade in the room to maintain all these relays operating optimally. And today, the temperature needs to be a bit cooler, just cooler than the outer space. Hence why we have these very big fridges that encapsulate the micro, the superconducting processor that implements the qubits in this case. And all these apparatus around it to be able to control the way information flow in this machine. So here is where we are now. I think quantum computing technology is at the kind of moment where digital computers were in the 1940s. But we do not know what is waiting for us, as our forefathers did not know what we've got now if you looked at a room like that before. So, I'm going to repeat a little bit what Oliver already said, but I will start from a higher level. I'm not going to start from the level where the actual physics is taking place, but I will start from the level where, from what we call the level of abstraction, where we can use abstract formalisms to think about what's happening at the physical level. Because as we already mentioned a little bit, again, quoting Oliver, there are many technologies to implement the so-called qubit. Okay? That's why I will focus here on the abstract level rather than on which kind of qubit we are talking about. So, computers today, we all know, are binary, and it's based on switches. So the mobile phone you've got there, the laptop we have here, use exactly the same technology as the one that we saw in the 1940s. The only thing that evolved is the miniaturization and the sophistication of the switches. Instead of dozens or hundreds, now we have billions and billions of switches inside our smart devices. Now, you're talking about artificial intelligence. Well, AI is just software. And software that is running on machines that were invented in the 1940s. Now, just wait for AI running on quantum computers. It will be a completely different way of thinking, and this is what I find exciting. But let's look here. So this is the qubit. This is the smallest unit of information for a quantum computer. And we know already that qubits do not represent information in terms of ones and zeros, but in terms of what is called a state vector. State vector is that little line that's coming from the center with a dot. And this dot can point anywhere in this sphere. okay? And this is how a qubit represents information, which means that we can have as much information, in theory, represented in this qubit as there are possible dots in this sphere. So it's not only 1 and 0, but more 1, more 0, bits, shades of 1s and 0 in between. If you are at the equator line there, this qubit is 50% 1, 50% 0. If it's a little bit above the equator, you can say, well, this qubit now is more 0 than 1, and so on. And this is the big difference. And the thing is that all this obeys the laws of quantum mechanics, right? And in quantum mechanics, we saw already you have cats that are dead and alive. We have things that we don't understand in the world that we live here. So it's a very weird world. And what we do in quantum computing is to harness this weird world to do things for us. This is another metaphor, which again is probably very wrong from a physicist point of view, but it helps me to explain to my students what a qubit is doing. So we imagine that you have a qubit as a spinning coin, okay? And you do computation with this qubit while the coin is spinning. So you have many of these spinning coins in your machine, and you do the computations while they are all spinning. But when you read them, again, the wave function, remember? When you read these qubits, they will always return a binary value to you, either 0 or 1. But the art of programming the qubits is the art of doing the processing while they are in this state of superposition, which is, in this case here, while the coin is spinning. So I find this a very intuitive and easy way to try to visualize what's going on, although it may be completely wrong for a quantum physicist for me to say this. Again, before we move on, this is an abstraction of the qubit. By the way, this is called the Bloch sphere. Thanks to Bloch, who was the physicist who proposed this abstraction. It's a way to try to visualize what a qubit may be like. It's nothing like this, but abstraction, it may be, it's a way of thinking. And the sad thing about it is that it is valued, it has a value for 1 qubit. Once you have more than 1 qubit, then this sphere disappears. You can't think about it because the dimensions are more than 3. Here we go. Qubit and the state vector. That's important because it's something that will come again and again in my talk. The state vector is this thing here that comes from the middle there and is pointing to different places in the globe, in the sphere. So let's have a look now at some kind of more technical sides of things. So here we have a fantastic quantum computer with 3 qubits, right? So I represented the 3 qubits here on the left side. And what you see at the top there is called a circuit. Circuit is what physicists call a computer program, right? So whenever you see, oh, I'm going to design a circuit, oh, what the hell, what's circuit? No, it's a computer program. For computer scientists, this is a computer program. And again, the level that we are today at programming quantum computers is a very low level. We are thinking about manipulating qubits as 40 years ago, 70 years ago, we were programming machines in terms of plugging switches, right? Now we have very high level programming languages to program computers. We don't care about the bits anymore. In the very near future, we won't care anymore about qubits because you'll be using programming languages that are on a higher level, and we'll be doing things that we don't need to understand what the qubits are doing at the lower level. But for now, because there are not so many qubits out there for us to work with, it's a good thing to visualize this in terms of these circuits. So what's happening here These squares with letters inside, they are the commands of the quantum computer programming language, if you wish. And they do things to the qubit in a sequence, like from left to right. But again, this is wrong, because this does not happen in sequence. It happens instantaneously, right? To think about sequencing actions is a way that we need to think about in this way, because that's the way our brain works. We need in terms of steps to achieve, to get an algorithm working. But for a quantum machine, there is no sequence. When you run this, it's immediate. So all these things that are in sequence here happen at once. So what's happening here? So we have this X commands and an H command. And then there are some other things that are happening there. And then where we have those dials, it means when we read the program, when we observe the program, when we see those little lights going through these slits that we saw the animation earlier. So the back thing that gets the dot or the electron, this is what we do there. Ooh, what happened? Oh, nothing, okay. Probably because I've got this in my pocket. So I'm going to show you the steps now. And remember, this is not sequence, but didactically, we'll do it in sequence here. So the qubits start in what is called the ground state, normally. The ground state is the zero kind of thing, right? All these vectors pointing to the north. Then we begin to run the program. What is happening here? Well, the X command tells the qubit to invert the state vector. It's the equivalent of the NOT gate in our logics, in the digital logics we've got today. So I'm just saying, put these 2 qubits down, and the H gate is the interesting one here. It's called the Hadamard gate. It puts the qubit in an equal state of superposition, which means put the state vector in the equator line, right? Because at the end of the day, when I read this, when I read the circuit, there is a 50% that this qubit will return 0, and 50% that you return 1 to you. But for example, if I don't put it in the equator line, then this situation changes. There is a higher chance, if it's below the equator line, is a higher chance that you return 1. Higher chance is not certain. Or if it's a little bit above the equator line, there is a higher chance that you return 1. But again, this is all probabilistic. Is a higher chance, but we do not know until we actually read it. So what's happening here now? Let's follow what this program is doing. Right, so we do not know what the H gate will return you, right? So if it returns 1, other things happen there, which I'm not going to explain right now. The result will be 0, 1, 0, 1. But if it returns 0, the result would be 0, 1, 0. Okay? Now let me explain what are these things in the middle there. So the dot at the bottom line means a condition, right? Something will happen to the qubit that is above it with that cross, the round with the cross. Something will happen to it only if that qubit there is 1. In the previous case, something happened to that qubit there because the result of the H gate was 1. And then subsequently, nothing happened to the top one because that was 0, so that one continued to be 1. But now, in this case, nothing happened to the second one, to the middle one, because it returned 0. But then, because the X gate flipped the state vector to start with, then it will flip the state vector of the top one back to 0. You see the logics behind quantum computing here? All this happens at once. This means that with this little program, you can ensure that the machine will return to you only two kinds of results, or 0, 1, 0, or 0, 1, or 1, 0, 1. Let's look at a practical application of this, and then from here we'll go to music. Imagine you have a problem. This problem is there are many pathways that you can follow, but some of them are better than others. Okay? So some of them you have a lion waiting for you, and the other ones you have some bags of money, right? So this is how good and bad this can be. So there are three options for good ones here for you. The option is 0, 0, 1, 1, 0, 0, or 0, 1, 0. The others you don't want for this program to give you. So you throw dice, let's say, then you get these numbers, and then you follow what the dice tell you what to do. So if you want to program this on a sequential computer, again, remember the asking many questions, the same applies here. You throw the dice, but you follow what the dice say only if the result is one of the nice ones. Okay? This means that you have to throw these dice as many times as needed until you get a result that you like, the look of. So this is the way of programming this sequentially. Now, this is only three options. Imagine a problem, let's say in an airport, where you have airplanes coming in, gates, and bags and stuff. You have many things happening, highly combinatorial problems, and you need to find pathways through this maze. So this is where a quantum computer is good for you. Because if we represent this problem in terms of a circuit, the moment you measure it, you get the result that's good for you. Right? So I represented the three numbers, the 3 bits there, the binary options, okay, with the top 3 qubits. This is a 5 qubit computer. And at the bottom, I have 2 qubits that function for me as a kind of a dice. Remember the Hadamard gate? There is a 50-50% that you go up or down. So this is what happens here. For example, if I am in 001, you read it from bottom up. If I run the circuit, if I measure it, the dice will be thrown in certain ways that is guaranteed that at the end, I will get only one of those 3 that I want. Let's follow an example here. If it happens to be 1 and 0, then with this gate there, blah, blah, you flip this, flip that, boom, you get a valid result. And so on. So let's go to music now. Now where things begin to get more interesting. Because all this was to introduce you to the thinking about solving problems where you have many alternatives, many pathways, many combinations. And this is why a quantum computer is good for us, because we can process all these combinations without having to ask many questions. The same way that we have that cube problem, when we program machines to do artificial intelligence for us, we program machines to follow rules. And there are rules of composition that have evolved through the ages, and there are rules that we make ourselves as composers. So today we have a flexibility to invent our own rules. But nevertheless, music follows rules, even if it's intuitive. There are always some structure there which are governed by the way things are organized. And the way things are organized follow rules. Here is a very simple musical system where I have, let's say I have a bag full of measures, right? And I take these measures and put one after the other. like dice in a kind of game or Scrabble or something. But because, where did I put the thing? Oh, here. Because music has rules, there are some rules here that tell me that some sequences in this bag are not good, but some others are. So instead of taking the things out of the bag one each time and see, oh, is this the right one? Is this the right one? Now I can run a quantum computer that tells me exactly, gives me first time the one that is good. And here is a nice way to formalize the problem. Again, the metaphor of the sequential thinking. Because computers today are quite fast, these kind of simple problems here seem very fast to us, seem quite instant. But in truth, the computer is processing all these in sequence. The Turing machine. A Turing machine is a sequential machine. That's the fundamental of all computers. Now, if I program this with a circuit exactly the same as I did for the cube, I can begin then to say, okay, I have this measure here. There are some that are good to follow, some that are not. Run the program. Okay, I got another measure. Run the program again. I got another measure, and so on and so forth. There we go. So it's the same way of thinking as with the cube. I will skip this. Now, let's go to music and the way I've been using it myself, and I will briefly touch upon how my colleagues and collaborators in my lab have been using quantum computing to create. One way to use machines to create music is to program them to generate patterns for you. Okay? For me, there are two major ways of programming computers to generate music. One is to use AI. Well, yeah, a kind of AI, a system that you give a lot of information to it, then it learns some rules, and then it composes imitations of the stuff that you use to train the computer. Okay? I'm not interested in that, because I'm not interested in copying other people's music. Parrot, ChatGPT, they're all parrots. They're all imitating, combining things without knowing what this combination means. So that's one way, fine. But there is another way, which is to program the machine with algorithms that generate patterns for you, and patterns that are not necessarily the ones that you would come up with by yourself, by hand. And this is the beauty of machines, that they can do things, they can liberate you from repeating yourself by surprising you. And this is how quantum machines are being, that's why I find them very exciting. So I write circuits, right? Some very large ones. Some of them cannot be simulated on classical machines anymore because they are so large. My Macintosh here struggles if I try to simulate more than 20 qubits in it, right? So if I have a program here with 50 qubits, they won't run on these machines anymore. And that means, oh, wow, I'm generating a pattern here. I have a computer program that gives me stuff that only a quantum computer can give. This is already very exciting. So what I do, I have this, and then, of course, at the end there, depending on the initial states, I'll get a string of 10, 10, 10, 0, 0, 1, whatever. And I have a huge dictionary that I can build that will translate these patterns into some sort of musical form. Okay? And then I take this, and I write a musical score with it. What do? I take those three first notes there, and I distribute them in time. I made either a melody, or play two and another one, or distribute them between different musical instruments, etc., etc. So here is a real interaction between what a machine provides me and what, as a composer, how I interpret and how I use this creatively. So that's one way. Unfortunately, this style of composition is not going to be performed here tonight because we don't have a chamber ensemble to play it. But there are other things that we are going to show. For example, this kind of thing. So we have been developing systems that listen to people playing, okay? And then the computer is still classical, okay? Will make these rules for me. It looks in the music and it extracts, so this one follow this one, 50% more than this one follow this one, or later on this one appeared more times than this. So it builds a framework, a statistical framework, which then is very easy to convert into quantum circuits. So I extract rules of composition from what it hears, and then represent those rules in terms of quantum circuits. And then every time I want to produce a sequence of stuff, let's say in response to what has been played, I communicate with a quantum machine through the cloud to process these rules and give me some results. So that's a truly interaction between musician and quantum computer, almost in real time, because in fact, quantum computers are not as fast as we think. They can process information in parallel, but the actual act of processing is still a bit slow. We counted about 5-6 seconds for each of these interactions. But nevertheless, it's interaction. We are interacting with a machine that operates in with the laws of quantum mechanics, and this is different. So this is the kind of score that I write for, so I know this is a continuation of this piece here, really. It's another instance of this piece, where I've got here a session where I let the computer to listen to the violin. Then while the violin is playing, the computer is building these circuits and sending to the quantum machine. Then the quantum machine produces a response, which I synthesize using another instrument. For music tech people in the audience, all this information is translated into MIDI information, which I then use to play a synthesizer or other things. Now, this is the exciting thing that we are going to show tonight. We have been working for a while now in a kind of an instrument that we call Q1 synth. It's a 1 qubit synthesizer. It's 1 qubit for now, but it will be more later. As a prototype, we developed this system where we've got this representation of the qubit in the center screen there, and then we can. You see the red dot at the top. That's the vector. And then we can rotate this sphere, either with gestures, as we will see tonight. Federico is going to control a few of these synthesizers with his gestures, but we can use the mouse, we can use any MIDI controller we can use to rotate this qubit. As we rotate the qubit, it creates what is called quantum states, but we are developing methods to synthesize, to sonify, if you will, the quantum states. So in effect, what you've got here is an instrument that you are interacting with a qubit, and as you interact with the qubit, you hear a musical interpretation of how this qubit may sound like while these quantum states are being created. But make no mistake here, while you rotate this qubit, you are not rotating the qubit that's in the machine there. What you are doing, you are rotating the qubit represented in your laptop here, right? But when we measure, you see the button measure there, when we measure this qubit, then it builds the circuit that represents that particular quantum state at that particular time, sends to the machine, and the machine will tell you, go up or down. It's very simple. But in this process of going up or down, it makes a kind of the real sound that is a measurement of that quantum state. Again, metaphorical. It's all very metaphorical because measurement happens so instantaneously that what we do here, we kind of slow down in slow motion to make it more artistic. Okay. Yeah. So the first composition is called swirling qubits. We will have 4 of these synthesizers. It will be shown on the screen here. And Federico is going to move, and we managed to connect his gestures in some meaningful way that you can hear what he's doing, and you know, wow, what he's doing here is creating quantum states. We are listening to these quantum states. We are, interacting with this world. Then after the first piece, there is the second piece, which is called Rever by Paulo. And this one is a very interesting piece because is a telematic piece where we build on this concept of communicating online with other worlds. Okay, so Paulo, you'll be communicating online with the quantum world to create quantum states that are representations of sound. We are developing ways to represent sound in terms of qubits. Imagine this. It's not samples, ones and zeros and ones and zeros, but the actual sound will be represented in terms of these qubits. And as you measure the qubits, you get variations on the sound, right? So this is what Paulo started doing with his composition. So he inputs sounds, creates these quantum states, then he measures, and then these measurements he sends to his friend in Brazil, in São Paulo, who has a fantastic studio full of analog synthesizers. So all these measurements are converted into voltages to control these synthesizers, which we will be listening to in real time here. So it's a truly different way of thinking about deploying these representations, quantum states, and communication with other worlds. Then we have the other piece, the third piece, which is by Paulo and also Pete, that's work in my lab. And here again, they are communicating with a quantum machine to create algorithms, almost this kind of thing here. Almost this kind of thing. But they are creating these algorithms as live coding. You're familiar with live coding, right? So they are doing quantum programming live coding, quantum circuit live coding. And then they build these circuits, they send to the quantum machine, get results, and then Pete has an algorithmic generator that converts all these things in sounds in real time. So again, it's an instrument that is interacting with a quantum machine. In the fourth piece is a more adventurous piece. It's an experiment that we began to do in my lab just a couple of months ago. It may work, it may not work, we'll see. We are trying to connect our brains with these qubits. Okay? And I think here, we are beginning to touch something that may be quite interesting in the future. We do not know yet, but we know that brain-computer interfacing technology is evolving very fast. And the bandwidth for connecting with quantum machines, as we have today, is very narrow. We still connect with them with these keyboards and things. But is there a way to connect our thoughts straight away with these new machines? So there probably will be. People have not started doing this yet, but musicians started doing it. So we are already investigating this. And fingers crossed, we will be able to make a little demonstration later on today. And a little bit of advert. So the propaganda side of the talk. I edited a couple of books. If you are interested in computer music, that's the one to read. I think there is a collection of chapters by people who are pioneering this field with us. And the other one is a little bit more theoretical, more philosophical interpretation of quantum computing in the humanities. Here we have filmmakers thinking about quantum film. We have philosophers trying to make sense of quantum technology from a philosophical point of view. We have people thinking about social sciences, using terminology from quantum mechanics and so on. So there are things that are beginning to evolve outside the scientific lab based on those ideas. And I think this is where things begin to get very interesting. And yeah, so I think I will stop here. Is there any more? Oh, there is this. So this is, again, another propaganda thing. I've created a PhD program in my university. It's probably the first one on this topic ever. I have no idea who is going to be the evaluators of this thesis in 4 years' time. There may be people out there that in 4 years' time, if someone starts a thesis now, there is already a person doing a PhD in this. So fingers crossed, we are going to evolve very fast. And yeah, so I'd like to thank IQM. IQM is a company based in Finland who is providing us access to their machines. It's incredible. It's one of the very few companies that provide access that are not for scientific purposes. And this is really good. And I shall mention Moth, which is a company that I've been involved in creating, based in London. It's probably the first company in the world that is dedicated to developing quantum technologies for the arts. So it's just started. Last month, we got the investors putting money in it. So watch this space. And of course, my university for providing me the platform to develop this research and support what we are doing, and above all, believing that this is possible. Thank you. Do we do questions now or later, or don't know?
Yeah, we can take...
Maybe later.
No. I think there is no later, but we can do now for 5, 6, 7 minutes.
So I want to say,
the max.
Yeah, just please stay for the concert. It's going to be quite interesting, and all the team will be here after the concert to talk to you. Okay? I don't want to give a lecture about the music. Now, there is going to be no introducing the pieces. We are going to play them. I already said a little bit what they are all about, but I think we should approach this from the artistic experience, from the experience of, from what you experience in the concert, what you see, and then make the questions based on that. And we'll be all here after the concert to talk. I think that's the idea.
Okay, great. Thank you, Eduardo. So that means we have about 15 minutes break. We start with the next part at 5:30 straight. Yeah? Okay.
Thank you so much. Thank you.